All right, welcome to part 3 of chapter 2. I'm going to tell you about a couple of my favorite scientists, one of whom you know, and one of whom you've probably never heard of. So Isaac Newton, Sir Isaac Newton most properly, invented calculus so that he could actually write down physics, right? So he could actually write it down. And that was, that sort of mathematicians, physicists both go, wow, when they look at that. Now, Newton, on the other hand, didn't think it was ever going to amount to anything. He thought it was a great exercise. He loved doing it. He did some physics afterwards. He met some mathematical challenges afterwards, all for fun, but he didn't really think it was going to matter a lot. So Newton went off and got a real job, as he would call it. He became Exchequer of the Royal Mint. And one of the things he did was he invented the little ridges on the edges of coin that kept people from trimming off the edge of coins. Got to remember, in his day, coins were made out of really precious metals. They're made out of silver or gold or something like that. So, the fact that he did this actually saved the crown a lot of money. Now, this physicist you've never heard of, Gabrielle Amélie Letonlier de Bretuel Marquis de Châtelet. She is astounding once you know her story. Astounding because she was a woman, and because she was a woman, she was not allowed to go to university. So what did she do? She hung out in the halls. She hung out in the halls and she listened to the lectures and she took her own notes hanging out in the halls at the university. And she took Newton's Philosophiae Naturae Principia Mathematica, and she translated it into French. And while translating it into French, she fixed a few things here and there. She wasn't just translating, she was taking the math and she was working through it, and she fixed a few problems he had around light and some of his issues with gravity, and basically tidied it up a bit. And then, again, she's a woman. She did not have an academic career. She was the wife of the Marquis. And so what did she do? She put it all in her dresser drawer. She died in childbirth. No one knew she had done this. And then 9 years later, they find her manuscript. Her manuscript, the translation she did of Principia Mathematica, is still the official French translation today. So you got to remember, she had no formal education, and she took Newton's work, she went through it, she translated it, she fixed some pieces here and there, and her translation still stands as the best there is today. Alright, so both of them, one of the things Newton had to treat was gravity. Now, the acceleration of gravity, and this is where we will often have confusion over signs. We'll talk about the acceleration of gravity all the time. The acceleration of gravity is always down. So the acceleration of gravity is 9.8 meters per second squared, roughly. We're not going to use too many significant figures here, but 9.8 meters per second squared. If we consider up to be positive, then this corresponds to an acceleration in our equations of minus 9.8 meters per second squared. And you're going to say, hey, wait a second. We had accelerations, we had equations in x, and now we're talking about x, east, west, horizontal. Now we're talking about up and down. Well, all of these equations still apply. They're still the same equations. Now, instead of saying in the x direction, which by convention we call x this way, we're going to say y direction. All right, we're going to say we're going in the y direction. We're talking about gravity now, and we're just going to rewrite all of these using y instead of x. So now we've got our acceleration, minus 9.8 meters per second squared. Now, if we were to do something silly and consider down to be the positive direction, it would be plus, but we're not going to do that. So, if we start a problem, and we often start a problem by saying wherever we start at, we're going to call y equals y naught, our starting point, 0 meters. We're going to solve our starting time, 0 seconds, right? And we take this ball, this guy's throwing a ball or a rock or something. We take that rock and we're going to throw it up, an initial velocity of 13 meters per second, right? It's going to go up. As it goes up, it's going to be decelerating because the acceleration, right? Its velocity is up, but the acceleration is down, right? So it's going to be slowing down as it goes up. And it's going to get to where it comes to a stop right there. And then it's going to head back down, all right? And it's going to be accelerating as it heads down. Any idea what velocity it's going to be at when it gets right even with where it started? Well, its velocity is going to be minus 13 meters per second. Right? You've got this deceleration from 13 to 0, and then deceleration down from 0 to minus 13. So this acceleration brings it right back to the exact same speed. Right? Exact same, and the velocity is in the opposite direction. Something you've done over and over again with a ball at some point. So we stick this in the equations. All right, so stick this in equations. There's our minus sign right there, right? Because gravity is downward. And so y is minus 1/2, 9.8 meters per second squared times time squared. Plus, here's our initial velocity, 13 meters per second times time, plus our initial position, which we chose to call 0. This is the equation for the height of the ball versus time. If we go to part B and we start off with our initial velocity down, all right, and say our initial velocity is down instead of up, well, now both of our acceleration is negative and our initial velocity is negative, and that's the only change to the equation. Everything else stays the same. This gives us a nice little formula that we can use for predicting where is the ball going to be at some future time. And that's one of the important things about physics. We're trying to come up with a mathematical description of the world that lets us look into the future and predict what's going to happen. Right? Let's look at our equations again. So here we are. We have a known starting velocity. We have a known starting position. What we want to do is we want to be able to take things we know, and the physics of what's going on, and predict what's going to happen at some future time t. As time progresses, what's going to happen? This is one of the chief things we're trying to do in physics, is use the physical laws to look and see what will be happening after we start the problem. All right, that's it for this section, and we'll come back in a minute for a little bit more about graphical techniques.